Hey, good morning, guys. Assalamu alaikum. Welcome back to Inspired Teens Grade 11 Physics/Chemistry. In today's lesson, we are going to be discussing acids and bases. Okay, a really important section that you need to understand really well, and that leads into grade 12, because in grade 12, you'll be doing the exact same acids and bases plus like pH, which is just a little bit like a slight extra bit. Okay. But your understanding of grade 11 is very important and plays a crucial role as well in grade 12. Okay, that being said, let us start. Okay. Okay, so acid and base definitions. Okay, so there's two different acid and base definitions that we need to know. Okay, the one is from Arrhenius's theory. Okay, and the other one is from the Lowry-Bronsted theory. The first one we're going to discuss, okay, is the Lowry-Bronsted theory. Okay, we're just going to read it and then we're going to try and understand it in terms of this reaction. So here we have Lowry-Bronsted stating that an acid is a proton donor, okay, and a base is a proton acceptor. Okay, so this is what Lowry-Bronsted says. An acid is a proton donor and a base is a proton acceptor. Okay, so a proton is an H plus ion. So let's have a look at this reaction and let's see if we can try and identify our acid and identify our base. So we have HNO3 plus H2O as reactants. Okay, and on the right hand side, our products are NO3 minus plus H3O plus. Okay, so in this case, let us try and observe basically what happened to each reactant and what did they become on the right hand side. So if we look at HNO3, okay, HNO3 becomes NO3 minus, okay, while H2O becomes H3O plus. Interesting. So what happens is HNO3 loses its hydrogen and H2O gains a hydrogen. Okay, so this guy, let's use this, HNO3, okay, it donates its hydrogen to water. Okay, and we can clearly see that hydrogen receives H2O receives the hydrogen and it becomes H3O plus. So this H2O, okay, H2O, we can see that this received H plus. Well, let's just say receives. Okay, so according to Lowry-Bronsted theory, an acid is a proton donor while a base is a proton acceptor. So in that case, the one that donates is going to be called the acid, and the one that receives is going to be called a base. Okay, so the further proof, how do we know for sure that HNO3 donates? Because we can see that HNO3 becomes NO3 minus. It loses that hydrogen, which means that it donated it to H2O. And then we can also see that H3O plus, H2O, it definitely received that hydrogen because it became H3O, this extra hydrogen instead of H2, it became H3O plus. Let's talk about the charges, okay? Where do these charges come from? So a proton, okay, is an H plus atom. Okay, so it's already charged. It has a one singular positive charge. So when this HNO3 loses that singular positive charge because it's giving away a H plus hydrogen, it would become one negative. Okay, that makes sense because it's donating an H plus ion. Then it itself would become 1 minus. Okay, and then the one that's gaining the H plus would now gain an extra charge and would become +1. This is -1 and +1, which we don't write the ones, but that's what they mean. Okay, so yeah, these are obviously neutral initially. And that's why they become negative and positive respectively. The one that had lost the H plus would become 1 negative, and the one that had gained the H plus would become 1 positive. Okay, so yes, this is acting as an acid, this is acting as a base. Now let us discuss acid-base conjugate pairs. Okay, so to be able to identify the acid-base conjugate pairs is really simple, because all you have to do is pair up on the left-hand side and on the right-hand side 2 compounds. You have to pair up, let's just start HNO3. So this is the first way for us to tell what's the acid and what's the base. Okay, identifying an acid and identifying a base. According to Lowry-Bronsted, an acid donates, a proton receives. In this reaction, we can clearly see which one donates and which one receives. So therefore, we are able to identify the acid. The acid is HNO3. The base in this case, the one that's acting as the base, is H2O. Okay, cool. So now, what is this acid-base conjugate pair thing, right? So it's easier to identify, like I was saying. You just have to, let's just say we're working with HNO3 and we want to understand what's the acid-base conjugate pair of HNO3. Whatever it becomes on the right-hand side would be its pair. So HNO3 becomes NO3 minus. HNO3 becomes NO3 minus. And in this case, right, when we form acid-base conjugate pairs, so let's write this out. We have acid base conjugate pairs. Okay, acid-base conjugate pairs. So it's a pair, okay, where one is an acid and one is a base. So if HNO3 is acting as an acid, whatever it becomes on the right-hand side would have to be acting as a base. So NO3 minus, in this case, is acting as a base. And these two, okay, these two are acid-base conjugate pairs. This is an acid-base conjugate pair. Okay, then the other one that we have is H2O. H2O is acting as a base on the left-hand side, okay? And whatever it becomes on the right-hand side, it became H3O plus. This would be acting as the opposite of that. And firstly, okay, it would be its conjugate pair. So this H2O and this H3O plus would be acid-base conjugate pairs. And this one is the base in the pair. So this one would have to be the acid. Okay, and this, again, these two are acid-base conjugate pairs. So an acid-base conjugate pair, one has to be an acid, one has to be a base. Okay, so once you've identified the acid or base on either side, whatever that compound was on the other side, left or right, would be the opposite. So here we've identified, for example, HNO3 as an acid, and whatever it becomes on the right-hand side would be its conjugate base. Okay, so that's how we can say. We can say that NO3 is the conjugate base of HNO3. Or we can say HNO3 is the conjugate acid of NO3. Okay, because again, in an acid-base conjugate pair, you have to have one acid, one base. Okay, so if you've already identified that one is the acid, whatever you then identify as its base, okay, would definitely be the opposite. In that case, once you've identified something as an acid, whatever you identify as its pair on the right-hand side would definitely be the opposite, which in this case is a base. Whatever you've identified as a base, once you've identified the base, whatever its pair is on the right-hand side, which is H3O plus, because that's what it becomes, is definitely going to be the opposite, which is an acid. Okay, and it forms an acid-base conjugate pair. Okay, I hope this makes sense so far. So please, if you have any questions, do feel free to ask me to clarify anything if you're still confused about this whole acid-base conjugate pair thing. Okay, but yeah, basically that's that. Okay, acid-base conjugate pairs we discussed, number one. Number two is we need to understand Lowry-Bronstet's definition of what? Laurie Bronstet's definition of an acid and a base. Don't worry about Arrhenius. We'll go through it in a bit. Okay, an acid is a proton donor. A base is a proton acceptor. Okay, so that we can clearly see here, this guy is donating, this guy is receiving. How do we know for sure? We can see what they become on the right hand side. Their products tell us, oh, okay, we can see that it lost its hydrogen and this gained the hydrogen. So definitely this donated and this received. So definitely this is the acid, this is the base. Right, let's identify conjugate acid-base pairs. HNO3 becomes NO3 minus on the right. That's definitely a pair. Since this is the acid, this is the base. Okay, cool. Then we identify the next one. H2O becomes H3O plus on the right-hand side. Since this is the base, this is the acid, and those are the two acid-base conjugate pairs. Okay, cool. Let's move on. pH scale we'll discuss later. I'll bring it back down to the other place. Okay, now we're going to discuss weak acids and strong acids. So we will be discussing strong acids, weak acids, strong bases, weak bases. You need to know the basic most common acids and bases. The basic most common acids and bases, strong and weak. Okay, we're also going to go through their respective reactions. Okay, so you'll see we learned that acids ionize while bases dissociate. Okay, so basically we are going to go, no, excuse the pun. Basically, we are going to go through the reactions for acids and the reactions for bases. Okay, that's what we're going to do. So we're going to start off on strong acids. We're going to go through some concepts of some bullet points of strong acids. Okay, so it ionizes, or strong acids ionize almost, we can ignore the almost, they ionize, we can just understand this completely. Strong acids ionize completely in an aqueous solution. Okay, ionizes basically means it separates into its ions. Okay, number two, it produces a high concentration of hydronium ions. Okay, so this producing hydronium ions is actually Arrhenius' theory, which we'll discuss. We're still going to discuss in a bit. But what we need to do is note the difference between strong acids and weak acids. That's the important thing. So strong acids on one hand ionize completely in an aqueous solution, while weak acids ionize partially in an aqueous solution. Partially means not completely. Then if we look, strong acids produce a high concentration of hydronium ions, while weak acids, they still produce hydronium ions, but just a low concentration. So it makes sense, right? Strong, completely, high concentration, weak, partially, low concentration. Then we have something called the Ka value, okay? Now, a strong acid would have a high Ka value, and a weak acid would have a low Ka value. So all like sort of make sense, right? Because they all like correlate with the word weak. What is Ka? Ka is simply, let's do this. Ka is simply what we call an acidity constant. Acidity. Okay, it's an acidity constant that tells us or indicates to us, okay, in basic terms, how acidic a substance is. How acidic an acid is. Let's just say something. Let's just say a substance. Okay, it tells us how acidic something is. Okay, so it's like an acidity constant. It's not something that we will work with in calculations, so it's not important for calculations, but we do need to understand that a strong acid would have a high Ka value. Okay, when we talk about high, the word high, hello, okay, we would refer to a Kc greater than 1. Any Kc greater than 1 would suffice as a high Ka value, and any Kc, any Ka, I'll go rewrite that, less than 1, we would suffice as a low acidity constant, a low Ka value. So therefore, any Ka value greater than 1 would mean it's a strong acid. Any Ka less than 1 would mean it's a weak acid. That's essentially what we mean. Okay, Cool. So let's move on to the reactions, right? We're going to start off with the strong acid reactions. And what we have here are ionization reactions. All of these are ionization reactions. Okay, the ionization reactions of strong acids. Okay, so before we worry about all of those things, okay, and all of that, let's just look at the reaction for what it is. We have HCl reacting with water to give us Cl minus and H3O plus. Okay, so let's try and use, what's this guy's name? Laurie Bronsted definition to identify our acid and our base. Okay, those answers are not there. Okay, so we have HCl again reacting with H2O that forms Cl minus and H3O plus. So HCl becomes Cl minus, H2O becomes H3O plus. So HCl is clearly the one that donates the hydrogen to H2O. Okay, and H2O is the one that receives it and becomes H3O plus. Okay, so that's why this is definitely an acid, while this guy is the base. Then we just pair them up on either side. So we know that HCl works with Cl. That's an acid-base conjugate pair. We know that H2O works with H3O. That's an acid-base conjugate pair. So that's why they indicated already our acid-base conjugate pairs. Okay, so that's Laurie Bronstet's definition. We can easily identify what's our acid, what's our base, and we can see the donation of the hydrogen and the receiving of the hydrogen. Now, let us discuss Arrhenius's theory. So Arrhenius's theory for an acid states, where are we? An acid is a substance that produces hydrogen or hydronium ions, same thing, H3O plus, when it dissolves in water. So it's stating that an acid produces hydronium ions when in water. So let's have a look. An acid in water produces hydronium ions. So we can see that Arrhenius's theory holds true for this acid as well. Laurie Bronstet's definition, as well as Arrhenius's theory, both hold true for this reaction, and we can use both to sort of identify our acid. Okay. So then we have, conjugate pairs, we can see which one donates, we can see which one receives, but we need to note that when we show the ionization of an acid, we need to form H3O plus ions, and that is indicative of an acid. When there is the formation of H3O plus ion, that indicates to us that it's an acid that has been ionized. Let's look at the second strong acid, common acid, HNO3. So the first one is hydrochloric acid. Second one is HNO3. Okay, HNO3 is nitric acid. HNO3 plus H2O gives us NO3 minus H3O plus. Again, we're forming these hydronium ions. Okay, not to be confused with what we'll learn in a bit, hydroxide. Okay, these are hydronium ions. So yeah. Okay, so again, we're showing the ionization of HNO3, which is nitric acid. In water, we can see that it forms H3O plus. And we need to know these reactions. We need to know how to write out these reactions. We need to know how to balance these reactions, actually. Okay, the first two, I think they're already balanced. Okay, because they can ask a question that actually requires one of these reactions as an answer. Okay, let's look at the third one. It's a bit more interesting. So the third one has two reactions, and more specifically, because if we see the first one, HCl, HNO3, but this guy is H2SO4. So it has two hydrogens, and it's a term, we refer to it as diprotic, okay, meaning it has two hydrogens. Okay, here we have HCl is an example of a monoprotic acid because it has mono one protic acid, protic hydrogen H plus, so one hydrogen, diprotic two hydrogen, triprotic three hydrogen. Okay, so going back here, let's have a look at, so these are ionization reactions, right? So what this refers to as you can see, we have a first ionization and we have a second ionization. So when it comes to diprotic acids, they ionize, they have two ionization reactions. Okay, so H2SO4 plus H2O. So what happens initially, okay, is this hydrogen donates, sorry, that acid donates a hydrogen to H2O and it loses a single hydrogen. It becomes HSO4 minus. So it still has one H left over, HSO4 minus. So obviously one minus because it just lost a single hydrogen. And this becomes H3O plus. This is known as the first ionization of H2SO4. However, if we look at what it became, H2SO4 became HSO4 minus. It still has the ability to donate one more hydrogen. That's why the HSO4 minus itself undergoes another ionization, HSO4 minus. Pretty sure this is incorrect. Okay, it undergoes another ionization. HSO4 minus in water donates the hydrogen, donates its H plus. Okay, and it becomes SO4. It lost its hydrogen now, that single one that it had. It becomes SO4 and 2 minus. Now you might ask why 2 minus? Because it was already 1 minus and it lost another positive ion. So that's why it becomes 2 minus. Okay, and then we form H3O plus again. So this is the double ionization reaction of H2SO4. Now this double ionization we can actually show in one complete reaction. That is H2SO4 plus H2O, okay, gives us SO4 2 minus plus H3O. So we can directly write the product or the final outcome. H2SO4 undergoes ionization and forms SO4 2 minus. However, when we do it this way, there is some balancing that we'll have to do. There'll have to be a 2 in front of H2O in order to balance, and there'll have to be a 2 in front of H3O plus in order, for us to balance. So there we have it. This is the double ionization reaction all in one step, okay, of H2SO4. Okay, cool. So let's have a look at this important statement. It says important, strong acids produce weak conjugate bases which don't react with water. Strong acids produce weak conjugate bases. So the key thing here is, may not make sense to us right now, but strong acids produce weak conjugate bases. Okay, so let's have a look at the first reaction. HNO3, this is a strong acid. HNO3 is a strong acid. Now we know, of course, HNO3, right? It has a conjugate base on the other side of the reaction. Its conjugate base is NO3 minus. So because NO3 minus stemmed from a strong acid, this in itself is a weak base, weak conjugate base. Okay, this in itself is a weak conjugate base. Let's do this. Okay, NO3 is a weak conjugate base. So the conjugate base that forms from a strong acid is always weak. Okay, this is important for us to know, and it will not react in water. Okay, strong acid. For now, we can just have a conceptual understanding. A strong acid produces a weak conjugate base. And now that's our strong acids done. Let's move over to our weak acids. But before we do that, we're going to discuss here, we're going to see that a weak acid, because this is an example of a weak acid. A weak acid is going to produce, firstly, it's going to produce a base, but it's going to produce a strong conjugate base. Let's rearrange that. Okay, so by the way, this is the base. We'll go through it again, but that's just to note the difference. Weak acids produce strong conjugate bases, while strong acids produce weak conjugate bases, right? Easy to remember, it's opposite. Now let's just revise weak acids. They ionize partially in an aqueous solution. They have low concentration of hydronium ions, and they have a low Ka value, right? They have a low acidity constant, less than 1. So we have the same process going on here, right? It's just now it's a weak acid. So the weak acid is still an acid. So it donates the H plus proton to a hydrogen. Okay, you'll see in all ionization reactions, you'll have hydrogen becoming H3O plus. This is of acids. All ionization reactions of acids, you'll have H plus or hydrogen water receiving an H to become H3O plus. So again, we have the same concept. We have this compound, CH3COOH, or also known as ethanoic acid, acetic acid, or your household vinegar contains ethanoic acid, right? So CH3COOH donates that H to hydrogen. Please do not confuse that it's not one of these H's. It's this H that it donates, okay? And it becomes CH3COO minus. And obviously this is the acid. I'm not going to write for all. This is the base. Okay, and it's a weak acid, so it produces a strong conjugate base. And here we have hydrogen that becomes H3O plus. Both definitions are true. It's still an acid. An acid donates according to Laurie Bronsted. A base receives according to Laurie Bronsted. An acid is a substance that forms hydronium ions when ionized in water. That is Arrhenius's definition, both all true. Then we have COOH2. This is also a weak acid. Also, we can write it as H2C2O4, or it's also known as oxalic acid. Okay, it's also diprotic. So you'll see that we have to balance the 2 hydrogens and the 2 H3O plus. Okay, that's actually very important. You'll see, okay, not for this year, actually for next year. Right, but that balancing is important. Nevertheless, this becomes COO minus 2. So it loses both its hydrogens, and this minus is inside, which indicates that the charge is twice. It's actually 2 minus overall. Okay, plus 2 H3O. So this is the ionization reaction of a weak acid called oxalic acid. Then we have carbonic acid, also diprotic acid, right? So we show that balancing. This forms a strong conjugate base, CO3 2 minus. Okay, this is known as carbonic acid. Important. Weak acids produce strong conjugate bases, right? We did one of the examples. Weak acids produce strong conjugate bases. Okay, let's move on to our bases. And let's note our differences between strong bases and weak bases. A strong base dissociates completely in the solution. So now we go to bases which dissociate. They don't ionize, they dissociate, okay? So strong bases dissociate completely in the solution, while weak bases dissociate partially in the solution, okay? Strong bases produce a high, this little brackets means concentration, right? We should always remember that. So I took a little bit of shortcut there. So I took concentration. And what is this? This is not the hydronium. This is now the hydroxide ion that we work with, hydroxide ion. Okay, so again, strong bases dissociate completely, weak bases dissociate partially. Strong base produces a high concentration of hydroxide ions. Weak bases produce a low concentration of hydroxide ions. Okay, a high Kb value and a low Kb value. So strong bases have a high Kb value. What is Kb? Kb again is now a basic constant. Let's get rid of this. Okay, Kb similar to Ka. This is a basic or an alkali constant. and it essentially tells us how basic something is. Okay, so a high KB value, again, we would be referring to what? A KB value greater than 1. And a low KB value, KB is a basic constant, tells us how basic something is. A low KB value would be a KB less than 1. Okay, same like Ka. So let's look at the dissociation of some strong bases. Strong base NaOH. Okay, strong base NaOH. So it's not as fancy as the ionization reactions. As you can see, we just show the dissociation in water. NaOH separates into its ions, Na plus plus OH minus. KOH is it gets K plus OH minus. LiOH becomes Li plus OH minus. So what's constant? We can see that this OH minus ion is forming, and that's actually this guy's definition, Arrhenius's definition. So Arrhenius's definition tells us that a base is a substance that produces hydroxide ions when dissolved in water. That's what Arrhenius tells us about a base. So we can see it here, right? This shows the ionization inside of water. Sorry, not the ionization, the dissociation inside of water. Okay, and we can see that the base produces these hydroxide ions when placed in water. So what actually happens is these two separate, okay, and that's why we have OH minus. Okay, so we can see that Arrhenius's definition holds true. What's important to note is strong bases produce weak ions, weak acid ions. Strong bases produce weak ions. Okay, so these are weak. These are strong bases. Okay, and then weak bases. Weak bases would produce strong conjugate acids. Okay, so let's have a look at weak bases. Again, dissociates partially, produces a low concentration of hydronium ions, has a low Kb value, less than 1, and we can show some weak bases. We can show their dissociations. Actually, there's a bit of an exception. There's an exception for NH3. Okay, why? Because NH3 actually ionizes. So this is a bit of an exception. Okay, but it's not too crazy. Right, the reactions are not like the most important part. The most important part is obviously our theory and getting our calculations down correctly. Okay, so this exception is that NH3 ionizes. So we can show the ionization of NH3 with water. Okay, when it ionizes, you can see that what happens is, in this case, NH3 is the base and water is acting as the acid. Okay, because NH3 becomes NH4 plus. So NH3 is the one that's receiving. NH3 receives from hydrogen. So hydrogen donates the H plus. Sorry, not hydrogen, water. H2O donates the H plus. Okay, and H2O, since it donates the H plus, H2O itself loses one of its hydrogens and becomes OH minus. Okay, so H2O is acting as the acid, NH3 is acting as the base, NH3 receives, H2O donates. This is the base, this is the acid, conjugate acid-base pairs. Okay, hope that makes sense. So that's just an exception, but we can look at the dissociation of another weak base. NH4OH separates into its ions, NH4 plus and OH minus. Again, note, weak bases produce strong conjugate acids. Okay, so while this is weak, this is strong. Okay, cool. Let's have a look at this. An ampholyte. Okay, so let us discuss what is an ampholyte. An ampholyte is a substance which can act as a base or an acid, H2O, then these are the main three examples, H2O, HSO4, HCO3 minus, and then we also have HPO4 2 minus and H2PO4 minus. So an ampholyte is a substance that can act as a base or an acid. An ampholyte is a substance that can act as a base or an acid. Okay, so what does that mean exactly? Let's just revise this chemical equations to try and help us understand what an ampholyte is. Okay, so here we have H2SO4 acting as an acid. Okay, H2SO4 acting as an acid. So its conjugate base on the other side is going to be this guy. H2,4 act as, okay, H2SO4 acts as an acid on the left here, and it forms its conjugate base pair is HSO4 minus. So here we can see HSO4 minus acting as a base. Okay, and then in the next equation, however, when HSO4 undergoes its ionization, we have HSO4 minus, known as hydrogen sulfate, acting as an acid. How do we know? Because we can see that it's donating its H plus to H2O. So HSO4 minus is donating a H plus, so it's acting as an acid. So here we have an example of how HSO4 can act as a base and can also act as an acid. Okay, it's generally a substance that has a hydrogen that can either take in another hydrogen or give that hydrogen that it currently has. Okay, it has to be a substance that has a hydrogen that it can give or it can take another hydrogen. Okay, let's look at H2O, which is another example of an ampholyte. In this example, we can see that H2SO4 is acting as an acid. So on the left-hand side, we have already identified our acid. So that must mean that H2O is certainly acting as a what? It's acting as a base. Okay, in all the acid-base ionization reactions, H2O is definitely acting as a base. Okay, because it's going to be the one receiving that H plus to become H3O plus. But now let's have a look. So that's in an acid reaction, in an acid ionization. Let's have a look at a basic ionization reaction. In a basic ionization reaction, what's happening here? This guy, NH3, this NH3 guy, let's get rid of this. Sorry. Okay, this NH3 guy, this is acting as a base because it's receiving the hydrogen from H2O. So that means what? That means that this H2O is acting as an acid because it is donating its hydrogen to H3O. So here we have H2O acting as an acid, but here we have H2O acting as a base. So that's an example of an ampholyte, a substance that in different scenarios, different chemical reactions, acid or base, whichever, depends, can act as either an acid or a base. And we saw it in HSO4 minus, and we see it in H2O as well, where in this acid ionization, it acts as a base, but in this base ionization, it acts as an acid. Okay, that's an ampholytic substance, an ampholytic, whatever. Okay, and it's known as an ampholyte, a substance which can act as an acid or base. H2O, HCSO4, HCO3 minus, main common examples, but there's also these, which you should know, HPO4 2 minus and H2PO4. Those are also ampholytes. Okay, substance which can act as a base or an acid. Now, we discussed this. HCl has one hydrogen, so it is monoprotic. H2SO4 has two hydrogens, so it's diprotic. H3PO4 has three hydrogens, and it's triprotic. Okay, and this is sort of just showing the double ionization reactions without all the other stuff, just a basic double ionization reaction and a triple ionization reaction. Okay, of each substance. Now, let's get to our very important part, acid-base reactions. There we go. That's better. Acid-base reaction. So far we've dealt with acids separately. We've shown their ionization. We've dealt with bases separately. We've shown their dissociation. But this section is called acids and bases. And now we are going to deal with reactions where we have an acid and a base. Okay, I know in the previous ones we had substances acting like an acid and one acting like a base. But now we are going to take each acid. So this actual base itself, strong bases, weak bases, whatever it is, okay, and strong acids, weak acids, and we are going to react them together. That's why acids and bases, right? We are going to react these substances together. So let us show these acid-base reactions. So in all of these reactions, there's 4 types, okay? In all of these reactions, we have something to do with a metal. We have a metal oxide, a metal hydroxide, and a metal carbonate. These are our bases, and then we have acids. Okay, so clearly, base and acid reacting with one another. Okay, so it's even written on top, right? Bases are your metal oxides, metal hydroxides, metal carbonates, NH3. Okay, those are our bases. And we have an example for each. So you need to, you need to have these memorized. You need to know that when we mix a metal plus an acid, we form salt plus hydrogen. You also need to know when we mix a metal oxide, which we'll discuss what it is in a bit. When you mix a metal oxide with an acid, you will form salt and water. When you mix a metal hydroxide with an acid, you will form salt plus water. When you mix a metal carbonate with acid, you will form salt plus water plus CO2. Don't worry, we're going to learn how to draw out this equation. What's the salt? What's the metal? What's the acid? Okay, for each one. So let's have a look at this. We have a metal plus an acid gives us salt plus water. Now, before we get there, let us look at this, the salt formation. How do we form our salt? Because, okay, let's draw out our reactants. So metal, Na plus, metal ion, Na plus, maybe can we use hydrogen nitrate, HNO3. This forms salt plus H2. Now, how do we form this salt? Okay, the salt is simple. You always form your salt with your cation of your base and your anion of your acid. So 2 things are important. The cation of the base is the positive ion of the base, and the anion of the acid is the negative ion of the acid. So cation positive, anion negative. Okay. And the second thing is the cation comes first. That's important. The order in which they're drawn is important. And the anion comes second. Okay. How can you remember positive cation, negative anion? Cats make you happy if you're not allergic. Okay. And onions, anions, make you cry. So that's negative. Okay. It's not the best way, but it's something. Okay. So cations, positive, anions, negative. Okay, and always remember. So the easier way I like to remember: anion, acid, anion, acid, anion, acid, anion, acid, anion, acid, and then you will never forget it. Okay, anion, acid, anion, acid, anion, acid, anion, acid, anion, acid. Okay, so yes, we form it. How do we form the salt? Cation of the base, anion of the acid. Okay, always, except some exceptions. We'll go through the exceptions in a bit, but for the most part, you are going to form your salt by taking first your cation of your base and putting it together with your anion of your acid. Quickly, let's just go through the exceptions. Okay, no, we'll go through the exceptions when we do the example. But for now, how do we form the salt? Cation of base, anion of acid. Cation of base, anion of acid. Anion of acid, a little bit, anion of acid. Now, remember, this is always our base. And this is always our acid. Okay, so we need to take the cation of the base and the anion of the acid. So we need to understand each different base and acid. We need to be able to separate. This is a grade 10 skill, okay? Being able to separate it, maybe even lower, grade 8, 9, I'm not sure. We need to be able to separate it into its cations and its anions. There is something very important called polyatomic ions. I don't know if you guys have heard it before. Many of you have probably ignored it up until now. Okay, but you need to know your polyatomic ion table. I will put it in these notes. Okay, they are very important because, for example, you need to be able to tell which two ions this compound is made up of. It's made up of an H plus ion. How do we know that hydrogen has a 1 plus charge? We get that from the periodic table. Okay, the group number gives us the charge, the respective charge of the ion of that specific element. How do we know the charge of NO3? That's from the polyatomic ion table. NO3, it's actually NO3 minus. So it's actually +1 minus 1. That's why when they join to form HNO3, those charges cancel each other out and we have NO3. Okay, if there was 2 or 1 or like a 2 or 1 or 3 or 2 or whatever, then it would have caused little subscripts. Okay, but for now, this example, it's important that that separates into H plus and NO3 minus. So let's identify the anion of my acid. This is my acid. The negative ion is NO3 minus. The base, in this case, it's just a metal. So it only has a cation. So that's my cation. My cation is Na plus. My cation of my base is Na plus. My anion of the acid is NO3 minus. So with that information, I can form my salt. I need to take the cation of my base and I need to form it with the anion of my acid. This is a single 1-to-1 charge. Not put a plus. Okay. I need to take the cation of my base, Na plus, and I need to join it together. This is basic compound forming with the anion of my acid, NO3 minus. And when I do that, I can see that it's a 1-to-1 ratio. So they're going to cancel each other out. I form my salt as NaNO3. This is now my salt. Cation of base, anion of acid. Cation of base, anion of acid. Let's do one more example quickly. Okay, we won't, but we'll just write out this equation because time is up. Sodium oxide. Sodium, if you want to know, this is just an example of a metal oxide. Sodium is made up of Na plus and O2 minus. How do we know this? Periodic table, periodic table. So to form its compound, you're going to have to mix the two. It's actually you cross it. Meaning the Na gets a little 2 and the O gets a 1, which we don't have to write because that's +1, that's -2. We cross it to form Na2O. Okay, and that's the final step we're going to take for now. So sodium oxide is actually Na2O. Geez, that's going to be annoying. Okay, and we'll just throw out nitric acid, HNO3. It's the same one, yeah. Nitric acid and hydrogen nitride, same thing, I believe. HNO3. Okay, we'll form the salt next week. Okay, cool. So we'll end it there, right? We made a fair bit amount of progress. You might be concerned why we didn't start like calculations yet, but there's a massive section, okay? And I want to treat it more strictly in grade 11. So by the time you get to grade 12, all of this makes perfect sense and you don't have to relearn all of this theory because it's very important, okay? You might find that maybe some acid and base questions are easier than others. Don't let that stop you from trying to understand the section completely because yes, you can have a basic understanding, get an easy question, and you won't need to worry about the more complicated understanding. But what happens if you get a complicated question? You need to understand the crux of this topic. Okay, so yes, there is quite a bit of theory. That's why we haven't gotten to calculations yet. Okay, so I hope that you guys understand. Please make sure that you understand all of this before we continue next week. So if it means rewatching the video or trying to do some theory practice questions, you can do the first few questions in most papers, right? Arrhenius's definition, Laurie Bronsted. Okay, by the way, while I'm talking, if anyone has any questions, please, now is the time to ask. There's going to be the next few minutes for you to ask any questions you want, whether you're practicing a question on this section, any other section. You can also unmute yourself if you'd like. Okay, so yes, that's why we need to have a good understanding of all of these before we continue, like strong acids, weak acids, strong base, weak base, ampholytes. Okay, especially also acid-base reactions in grade 11. I'm not sure grade 12, but in grade 11, you're definitely going to be able to, you definitely are required to know how to make this reaction from scratch. They'll tell you this metal reacts with hydrogen nitrate. In an acid-base reaction, you need to be able to form the entire thing, the products, the reaction, the reactants, as well as the salt, and know the product of each different type of acid-base reaction. Okay, so yeah, cool. So next week we will continue with, we'll finish the rest of the three, okay, doing examples of each. We'll just sort of like whiz through it because we did the main concept in the first one, and the concept applies for each other one, and we'll go through the exception of salt formation as well. Okay, that's I forgot to go through. We'll go through as well. Okay, and then we'll continue discussing salts, indicators, just some random notes. Then we'll move on to our neutralization, right? Neutralization, which is our first aspect of calculations, right? And then we need to discuss limiting reagent questions as well, dilution and volume change, perhaps like it might seem more than what you think acids and bases is for, but you really do need to know all of these things. And like I said, the better you know it in grade 11, trust me, the easier your grade 12 is going to be it's going to be easier to transition over to grade 12 and just add pH to it, which is actually quite simple. Okay, cool. So again, the session's still going to be open for the next few minutes. I'll end it at like 55, 56 to see if anyone does have any questions. Please, guys, do feel free. Please make sure you use this time to ask any questions, clarify any misconceptions. It's a free time. It's an open time. You are free to ask any questions. No question is a dumb question. No question is a silly question. Okay, so don't be shy. Even if you're on unmute, if you find that better, please start using this time. Okay. But yeah, for those of you who need to leave, you are free to leave. But for those of you who have a question, perhaps, or want to stay behind to hear the questions, you can. So yeah, cool. Actually, for those of you who are still here, can you please answer this question for me? What are you guys currently busy with? There's only a few of you left. But what are you guys currently busy with in school? My guess is it's not acids and bases because we are quite far ahead in the syllabus. It is a bit scary how far ahead we are. I think we're ahead anyway, because you guys should only be in like your second week, third week of school. And we are already in week 7, which is good though, because we're going to take like 3 weeks for acids and bases, which is nice. Very nice. Okay, someone says they're busy with stoichiometry, which makes sense. Quantitative aspects. Okay, the rest of you, yeah, what are you guys busy with? Okay, cool. Let's end it there. It doesn't seem like anyone else has any questions. So thank you guys so much for joining. Have a good rest of your week at school. And I'll see you guys next week. Okay.